Hello students, I am going to solve some more numericals on the radiation heat transfer. In this one, there are two large plates are maintained at temperatures 900 Kelvin and 500 Kelvin respectively. Each plate has area of 6 meter square. Compare the net heat exchange between the plates for the following cases. First one, both plates are black and have an emissivity of 0.5. And here for this one, the given data are taken. T1 is 900 Kelvin, T2 is 500 Kelvin, and area for both the plates 6 meter square. Now first, to find when the black surface is black, by using the epsilon 1 is equal to epsilon 2 is equal to 1 for that one, first case. Then net heat exchange between the two plates, this equation we have to use. Okay, this equation is the heat exchange between the two plates with emissivity considered. Okay, here the emissivity is considered this one. By considering that one emissivity, the equation of the heat transfer between the two plates, that is sigma A T1 raised to 4 minus T2 raised to 4 by 1 by epsilon 1 plus of 1 by epsilon 2 minus of 1. Then that can be substituted all the terms in this one. Okay, the area is given, and also this equation can be rewritten as the Stefan-Boltzmann equation as 5.67 T1 by 100 raised to 4 minus of T2 by 100 raised to 4. Okay, then substituting all the terms, that is 6 into 5.67 into 900 by 100, as temperature is given in Kelvin only, that we have taken directly. Then 500 by 100 raised to 4, 1 by 1 plus of 1 by 1 minus of 1. Okay, then we are going to get Q1 to 2 is equal to 201.9 into 10 raised to 3 watt. In the second case, where the epsilon or emissivity what is there, that is given as a 0.5, and if you consider that as the emissivity of the both surface as a 0.5, then Q1 to 2 can be given as sigma A T1 raised to 4 minus T2 raised to 4 by 1 by epsilon 1 plus of 1 by epsilon 2 minus of 1. Whenever the emissivity is considered, this equation we have to use. Okay, then this equation can be rewritten as 5.67 into T by T1 by 100 raised to 4, T2 by 100 raised to 4, like that. Then that after that one modifying, substituting all the terms, 6 into 5.67, 900 by 100 raised to 4 minus of 500 by 100 raised to 4 by 1 by 0.5 plus of 1 by 0.5 minus 1, that is equal to 67,300 watt we are going to get. Okay. The next problem, the sun emits maximum radiation at lambda is equal to 0.52 micrometer. Then assuming the sun to be a black body, calculate the surface temperature of the sun, also calculate the monochromatic mg power of the sun. Here we have to find out the temperature of the sun as well as the monochromatic mg power of the sun. Then the given lambda max is equal to 0.25 micrometer and 0.52 into 10 raised to minus 6 meter, that one. Then first one, surface temperature, monochromatic mg power, total mg power and maximum mg power in addition we can find out for that. From Wien's law we can write lambda max T is equal to 2.9 into 10 raised to minus 3 micro Kelvin, millikelvin, or we can write T is equal lambda max T is equal to 2898. Okay, that also, that equation we can use. From that here we can substitute that one. Okay, T we have to find out, lambda max we can substitute, and in terms of the meter this equation we are going to get. Then this we are going to get this equation. Then temperature will be 5576 Kelvin. Then monochromatic mg power, that can be given by the Planck's law, that is epsilon b lambda is equal to C1 lambda raised to minus 5 by e raised to C2 C2 by lambda t minus of 1. And this also equation we can take from the data handbook. Then that one, from that we can write here the C1, this term, the C2 are given from the data handbook only, the lambda already we are having, temperature also we have, and by substituting all terms we can find out the monochromatic emissive power as a 6.9 into 10 raised to 13 watt per meter square. Then total emissive power, that is sigma into T raised to 4, the sigma already we know, 5.67 into 10 raised to minus 8, then 55676 raised to 4, and that from that we are going to get, and maximum mg power, that is a 1.285 into 10 raised to minus 5 into t raised to 5. This equation also available in the data handbook, that we can use to find the maximum mg power. Then third one, a 70 mm thick metal plate with a circular hole of 0.35 diameter along the thickness is maintained at a uniform temperature 250 degrees Celsius. Find the loss of the energy to the surroundings at 27 degrees Celsius. Assuming two ends of the hole are to be parallel discs and the metallic surfaces and surrounding have black body characteristics. Okay, here the two ends of the whatever this diameter tube is there. Okay, in that one, the two blocks are connected at each end. Those two blocks are the whatever the circular discs are there, those are the black bodies. Okay, there the heat exchange between the two bodies whatever is there, that we have to find out. And the diameter of the whatever this circular hole is there, that is the diameter of the disc. Then R2 R3 is equal to 30 by 2, that is 17.5 mm is diameter, and the length is the distance between the two discs, that is given 70 mm. Thick metal plate is there. Okay, that thickness is also given. The T1 temperature is given, and T2 temperature, surrounding temperature, is also given. And from that, let suffix 1 designate cavity, and the suffix 2 and 3 denote for the two ends of the of 35 mm diameter. The two ends surfaces, and along the surroundings also the heat exchange is taking place. Then hole which behaves as a disc. Thus we can write here the L by R2, that ratio, and RT by L. These ratios are required to find the shape factors. To find that one, from that the shape factor by using these two from the data handbook, we can find the shape factor as a F223 is equal to 0.065. Then by the summation rule, F221 plus of F222 plus F223 is equal to 1, as F222 is equal to 0, as the whatever the incident radiation, that is whatever falling on that surface, that is equal to 0, itself is 0. Therefore F221 1 minus of F223, then 1 minus of F223 already we are having from the data handbook. Then we can write this F221 is equal to 0.935. Okay, then A1 F122, A2 F221. Okay, this is by reciprocity theorem. Okay, then F122 is equal to A2 by A1 F221. All the terms we know here. Okay, then by substituting that we are going to get F122 also. Then F123 1 to 2 is equal to 0.1168. By symmetry we are going to get this one. Then total heat loss. Then total heat loss of energy is equal to loss of heat by both ends. Okay, then A1 F122 sigma T1 raised to 4 minus of T surrounding raised to 4 plus of A1 F123 sigma T1 raised to 4 minus of T surrounding raised to 4. Therefore here F122 is equal to F123. Then here both are to be added to twice this A1 F122 sigma T1 raised to 4 minus of T surrounding raised to 4. Then here we can write that is a 2 into all the terms A1 and sigma whatever is there, that we can substitute. Then this equation can be termed as this by the Stefan-Boltzmann law. Then 6.8 watt we are going to get. Then another, the filament of 75 watt light bulb may be considered as a black body radiating into a black enclosure at 70 degrees Celsius. The filament diameter is 0.1 millimeter and length is 5 centimeter. Considering the radiation, determine the filament temperature. Okay, here the filament temperature we have to find. Okay, the enclosure whatever is there, its temperature is given, and whatever the filament diameter as well as length also given, and its capacity is given, heat generating capacity is given. Then we have to find out its temperature. Okay, this is Q is equal to 75 watt and T2 is equal to this one, D1 is this, and length is given this one, area is equal to pi dl. Then epsilon 1 is for the black body. Then whatever the heat is there, that if you consider that one, then we are going to write this equation 5.67 into 10 raised to minus 8 sigma is 1, the area of this one, the whatever the filament is there, that if you take, then T1 raised to 4 minus of 3, 43 raised to 4. Then by taking this one, T1 is an unknown value. Then by modifying this equation for getting the T1, that's after the simplification we are going to get T1 is equal to 3029 Kelvin. The T1 is equal to 2756 degrees Celsius. I'll stop here only and I will continue with the next problem in the next class. Thank you.